Now let's explain ethyne or acetylene, the bonding involved in this molecule using the concept of hybridization. Now if we see its structure, we know it's alkyne, so there will be a triple bond between carbon and carbon as it is appeared from its molecular formula, which is CnH2n-2, right? So as it is having a triple bond, so there is only one bond with carbon on each hydrogen. So moving on the same basis, let's find the hybridization around one carbon. Similar will be for the other because both of them are same. So step 1, we always find the total number of bonds around the atom whose hybridization we need to predict. So total number of bonds include all sigma and pi bonds. So you can see all the sigma and pi bond 1, 2, 3 and 4 around the carbon, right? So this means the first most important point is 4 half-filled orbitals are required in the valence shell of carbon to form 4 covalent bonds around carbon, right? Because we know half-filled orbital overlap to form covalent bonds. So this is condition 1, right? Second condition is to see how many hybridized orbitals required. So for that we always know that we have to see sigma bonds and the lone pairs around that atom. As pi bonds, see, hybridized orbitals are not used to form pi bonds. So sigma are 2 around one carbon and there is no lone pair. Carbon is using all its 4 valence electron in bond formation, so there is no lone pair on carbon. So the total is 2, which means that only 2 hybridized orbitals are required around carbon, right? So first of all we'll satisfy this condition and then we'll go for this condition to explain the bonding in this case. Let's see carbon in its ground state. You'll see valence electrons are 4, 2 in 2s and 2 in 2p. So this is the arrangement. So you see in the ground state carbon is having only 2 half-filled orbitals, right? So but we need 4 half-filled orbitals. So this means that in ground state carbon, we cannot imagine its hybridization in ground state until we'll fulfill this condition of 4 half-filled orbitals. So carbon has to move in excited state during the formation of bonds. So for that purpose, one electron from S will be shifted to a nearly same energy 2p orbital, so that there are, now you can see there are now 4 half-filled orbitals in the valence shell of carbon. But we know bonding cannot take place at this stage because these 4 are not of same energy and same shape, right? So we need to hybridize them. But before that, you can see this condition is satisfied. Now we are having 4 half-filled orbitals in the valence shell. Now we'll move on to the second condition, right? So in this case we need only 2 hybridized orbitals around carbon, right? So for that you'll see s orbitals are always involved in hybridization, being close to the nucleus, right? So as a result, in this case we'll involve only one s orbital and one p orbital because we need just 2 hybridized orbital, right? So one orbital of s and one orbital of p is involved in hybridization. So the hybridization here will be sp hybridization. That means 2 atomic orbitals are mixing and they're redistributing their energy to create 2 hybridized orbitals, which are no more s or p now, but they are sp hybridized orbitals. That is 2 hybridized orbitals around the central atom, right? So but at the same time we are having 2 unhybridized p orbitals, that is these 2 unhybridized p orbitals. Let's see, these will be used in the formation of what type of bond. Now before that, this is the situation around one carbon, that is 2 hybridized orbital and 2 unhybridized orbital, and you will see that these 2 will be used to form 2 sigma bonds around carbon, and these 2 will be used to form 2 pi bonds around each carbon. You can see around each carbon there are 2 pi bonds. So let's talk about the shape here. Around one carbon you are having one sp hybridized, another sp hybridized orbital. You know there are 2 hybridized orbitals around one atom, so that means the shape will be linear. They are linearly arranged to have a minimum repulsion between them. So this is situation of one carbon. This is one sp, another sp. Along with that they are having unhybridized p orbitals which are perpendicular to each other. these two, and both of them are also half filled, right? So this is situation of one carbon. Similarly will be the situation of the other carbon. It uses its sp hybridized orbital to overlap with sp hybridized orbital of carbon, forming a very strong sigma bond. Hybridized orbitals, they overlap with a great extent to form more stronger bonds as compared to atomic orbitals. So this is another sp hybridized orbital. Now this hybridized orbital will be used to form a sigma bond with hydrogen. Similarly here it is used to form a sigma bond with hydrogen with overlapping of 1s orbital. Now similar to this carbon, it is also having unhybridized p orbital which are perpendicular to each other, right? So as a result they are also half filled. Now you see, this is one formation of carbon hydrogen sigma bond, carbon sigma bond, and carbon hydrogen sigma bond. Now the sidewise parallel p orbital, they will overlap to form the required number of pi bonds, right? So this is one pi bond, this is explanation for the second pi bond. So this explains the formation of carbon hydrogen sigma bond, carbon sigma bond around the carbon, as well as carbon pi bond. So this is how hybridization is used to explain bonding in a molecule of acetylene.